In this lesson, we're going to continue our discussion of the rotating coil in the magnetic field, and our perspective challenges remain. So I first want to start off with giving you the perspective you're looking at in the image shown here at the top of your page. And the perspective you're looking at is now going back to looking at it from the axle rotating in that clockwise sense that we just discussed. So let me go back to the previous page of notes. Here's that clockwise rotation. So this is the perspective you're looking at. You're going to see the B field going off to your right. The coil is going to be at an in-between position from this lying flat with the B field and up to the 90 degrees. So it's in that first 90-degree rotation that we're looking at from this perspective on this page. So that is what you're seeing. This is the Roman numeral 1 person standing in the north pole of the magnet looking at the B field going away from them. We are now viewing it. So we view it from the number 3 position on page 12. And again, it's in between that lying flat rotation and rotating up to the 90 degrees. So we're going from that lying flat rotation, rotating up to the 90 degrees. And we had the two forces, right? F1 pulling up, F2 or F3 pulling down, and that's the two F's that we have here. It's the same F1 and F3. And what we're going to do now is zoom in here and calculate the torque about the axle. So this is my pivot point. And torque, yes, it is still from mechanics, R cross F. And the diagram we have here is R cross F. So we have the R vector going from the pivot to the point where the force acts as my vector R. The F vector is the force causing the rotation. When I take the cross product, I draw them from a common origin. So I have my magnetic force here. And the angle between the R vector and the F vector as the rotation is going to rotate from, as the coil is going to rotate from flat to 90 degrees up, the angle theta in the cross product is this angle theta. Now notice we are going to see in a moment that that angle theta is going to be the same angle theta that the n hat vector makes with the B vector. So we can look at the geometry, I hope we can look at the geometry and see that the n hat vector and the B vector are going to make the same angle theta. So we'll get to that in a moment as well. So R cross F gives us a thumb, do your right hand rule. R cross F, you're going to spin your fingers, you're going to curl your fist. Clockwise, thumb into the paper, so that's why I have it's a clockwise rotation down here for the torque. Clockwise rotation down here for the torque based on the current I1 only, so it's just the top current. And now let's take a look at the geometry we're given. Well, we have a little a and a little b here based on the rectangle. So let's go back and look at the rectangle. Little a and little b are given by a is the long side of the rectangle, b is the short side of the rectangle. As the axle runs through the middle of B, that is why we have R is B on 2, and A is the length of the coil that has the current I running in it. And that is an interesting thing to have in our R cross F equation. So we have R is B on 2, F is IL cross B, which is IL cross B is this. And we are going to note that the area A is given by little a times little b. That's the area. So we are going to replace little a and little b with the area of the coil, and we have a on 2 in our equation because we have the R had a 2 on it, so that 2 stays. And look at what we get. This is our kind of wow factor on this page of notes, because our R cross F boils down to the torque generated by just the current in I3 is 1/2 IA cross B because of this. So you have to make sure you see that the angle theta here is going to be the same angle in my cross product based simply on geometry, right? So if we look at the geometry, I've drawn everything from a common origin to try to help the perspective. The B is going to the right. The n hat vector is gotten by spinning your right hand in the direction of the current and sticking your thumb out, and it's perpendicular to the actual area, such that I'll have 90 degrees here. So theta plus phi is 90 degrees. Phi is 90 degrees. And I'll also have a 90 degrees with theta here and phi. So the two thetas are the same. And of course we have a current I3 on the bottom that also contributes. I'm not going to do, it will be the same exact mathematics we just showed. And we have 1/2 plus 1/2 gives us the net torque from a single coil is IA cross B. And the only other variation that you're going to see in problems is where you have a series of coils wound together so that the N in this equation is the number of coils if you have many coils to deal with. Now, you definitely do not need to know the derivation of the torque equals IA cross B, or N, if it's not many coils, IA cross B. But you do need to know the equation. You do need to know how to use it. You need to know that the n hat vector, based on what the torque is doing on the coil, always wants to align itself with the B field. So when this coil rotates to its upright position, the n hat will be perfectly aligned with the B field, and that is where we said there is no torque. So if the coil rotates through that position, the n hat vector now is down here and will again want to align itself back with the B field. So we'll talk about how it is that motors actually get the continual rotation, but for just the basic premise of torque and rotating coils, n hat vectors want to align with B fields always. Torque equals IA cross B, or sometimes I magnitude A n hat cross B. Okay, so hopefully you could follow the perspective and the logic with the torque, back to going through mechanics with R cross F to how we logically came up with IA cross B, and we will be using that to understand the rotation of coils in magnetic fields.